living in a nation almost swallowed by sand, where over 95% of the land is desert and rainfall is nearly non-existent. Saudi Arabia has achieved something truly unimaginable. The country has built a massive steel water delivery system that pulls seawater from the Red Sea to sustain an entire nation. Every day, billions of liters of seawater are processed through enormous desalination plants and pumped across the desert through a vast pipeline network stretching thousands of kilometers. While transporting water inland is an incredible engineering feat, transforming salty seawater into fresh water for drinking, farming, and industry is what earns Saudi Arabia global respect. So how is this invisible river of steel built and operated? Like, share, and subscribe for more amazing technology stories. Saudi Arabia is home to more than 37 million people, with nearly the entire population following Islam. What is especially notable is how densely the population is concentrated along the Red Sea coast and the Persian Gulf, while much of the interior remains an almost uninhabited desert. Although Saudi Arabia possesses what the world desires most, oil, nature never gives everything. Despite having over 40 trillion liters of oil beneath its soil, the country still spends billions of dollars to produce every single drop of fresh water. With average annual rainfall below 100 millimeters and summer temperatures regularly exceeding 45 degrees Celsius, survival demands innovation. To overcome these harsh conditions, Saudi Arabia built a nationwide water pipeline system using high-strength carbon steel pipes similar to those used in the oil and gas industry. Construction costs average around $3 million per kilometer, excluding booster pumping stations to support this vast pipeline network. Saudi Arabia relies on advanced desalination plants, each costing tens of millions of dollars. These pipelines draw water from a nearly inexhaustible source, the sea. However, seawater contains about 3.5% salt, making it unfit for drinking or irrigation. This challenge led to the development of desalination technology, giving the country a nearly unlimited water supply. Located along the Red Sea, each massive plant can convert up to 7 million liters of seawater into fresh drinking water every day. The first step in building a transnational water pipeline is manufacturing the pipes themselves. These pipes are made from high-strength carbon steel, similar to the materials used in oil and gas pipelines, allowing them to withstand constant pumping pressure, mechanical stress during underground installation, and extreme desert temperature cycles. Rectangular steel plates are cut to precise, pre-calculated dimensions, then rolled into circular pipes with an average diameter of about 1.8 meters and a wall thickness of nearly 25 millimeters. The plates are fed into a multi-axis rolling machine, where rollers gradually bend the steel step by step until both edges meet, forming a pipe blank. This blank is then joined through longitudinal welding. After welding, the pipe passes through a controlled water cooling line to reduce weld seam temperatures. Finally, the pipes are carefully ground along all edges and corners to remove burrs and ensure perfect geometric accuracy before proceeding to additional welding and inspection stages. The installation process begins at large staging yards along the pipeline route, where fully manufactured steel pipe sections are organized by diameter, length, and installation sequence. Engineering teams perform final visual inspections, checking pipe straightness, coating condition, and identification markings. Proper organization at the staging area is essential to maintain a continuous workflow, minimize delays, and reduce errors in harsh desert conditions. Meanwhile, survey teams establish the precise pipeline route using GPS systems, total stations, and terrain data, marking the alignment directly on the ground with stakes and visible paint. This ensures the pipeline follows the most stable and efficient path, avoiding weak soils, shifting sand zones, and erosion-prone areas. For pipelines stretching hundreds of kilometers, accurate routing is critical to long-term structural integrity. Before trenching begins, construction sites are cleared and leveled, and temporary access roads are built parallel to the pipeline for trucks and excavators. Welders and material transport vehicles rely on properly prepared desert sites, which include dust control and sand stabilization measures to ensure visibility and worker safety. This preparation is crucial for the smooth operation of the entire construction process. Once the route is finalized, large tracked excavators dig the trench along the marked alignment, maintaining precise width and depth for pipe placement and backfilling. Excavated soil is sorted on site, with suitable material retained for backfill and unsuitable soil removed. Consistent trench depth and alignment are vital to prevent pipe deformation or misalignment after installation. In sections crossing steep or rugged terrain, controlled explosives are used to carve trenches directly into solid rock, fracturing the bedrock along the planned alignment while ensuring safety and structural precision. The trench provides sufficient depth and width to securely seat the pipeline, even in areas where mechanical excavation is impossible, allowing construction to continue through extreme landscapes while keeping the pipeline buried, protected, and structurally stable. After excavation, the pipe is not placed directly on the trench floor. Instead, a layer of carefully selected material, typically fine sand or screen soil, is spread evenly to form a bedding layer. This layer distributes loads uniformly and reduces stress concentrations on the pipe. It is leveled and lightly compacted to achieve the required elevation, which is especially critical in desert terrain with loose, dry soils. For large diameter pipelines, a construction corridor approximately 40 meters wide is prepared in advance, enabling continuous installation at an average pace of about 1.5 kilometers per day. Pipe sections, roughly 18 meters long, are chosen to minimize field welds while demanding precise lifting, transportation, and alignment. At the welding site, a hydraulic system ensures exact positioning and secure joint formation. An internal lineup clamp is positioned inside each pipe joint and expanded with 360-degree gripping shoes to hold the two sections perfectly concentric and aligned during the root welding pass. An automated welding system, supported by roughly 80 skilled personnel and dozens of specialized machines, can complete up to 150 welds per day on 42-inch diameter pipes. Once welding is finished, each joint undergoes automated ultrasonic inspection to detect any internal defects. The field joint coating crew then performs abrasive blasting to clean the surface and applies a multi-component liquid epoxy coating, creating a fully sealed, durable protective layer. After coating, the assembled pipes are carefully lowered into the trench using side boom tractors, specialized tracked vehicles for large diameter pipeline construction. Multiple side booms operate in sequence along the pipeline, lifting each pipe section with padded slings and steel cables to protect the coating. The pipe string is evenly raised and suspended above the ground, ready for precise placement into the prepared trench. As the side boom machines move slowly along the trench, precise coordination between operators is essential to prevent twisting, bending, or contact with the trench walls. When properly aligned, the pipe is lowered gradually, centimeter by centimeter, until it rests securely on the prepared bedding at the trench center. Surveyors continuously monitor elevation, straightness, and natural curvature to ensure no residual stress is introduced. This method allows fast, controlled, and highly accurate placement, making it ideal for long, straight pipeline routes across flat desert terrain. After positioning, the trench is backfilled in multiple layers. A fine material layer is applied first to protect the pipe coating, followed by the excavated soil. Each layer is mechanically compacted to achieve the required density, minimizing future settlement and ensuring long-term pipeline stability under harsh desert conditions. The process begins by drawing seawater directly from the open ocean and channeling it inland, establishing a continuous supply of raw water for the desalination facility. Large offshore intake lines are carefully positioned and aligned by installation crews before being lowered into place using heavy lift cranes on barges or coastal platforms. As the pipeline extends toward the shore, individual segments are connected sequentially, forming a continuous conduit designed to operate under constant hydraulic pressure. Precision alignment is critical, as even minor deviations can impact long-term performance and flow efficiency. Once assembled, the intake line is reinforced with structural support frames and securely anchored to the seabed. The desalination process begins by drawing seawater through pipelines leading to open intake screens located a few hundred meters offshore. Barriers and intake filters catch large debris and prevent marine life from entering the system. A single 63-centimeter pipe can draw up to 15 million liters per day, over 10,000 liters per minute. Powerful pumps push the seawater toward the plant, but uninvited guests like jellyfish, crabs, and small fish can still arrive. To keep them out. Massive screens block anything larger than 4.5 millimeters, followed by finer screens to remove remaining large particles. Even after these steps, the water contains suspended sediment. Filtration tanks solve this problem by allowing water to flow downward through layers of sand under gravity. The tiny gaps between sand grains ensure only water passes through, leaving sediment and impurities behind. As water flows through the filtration tanks, suspended particles are trapped while the sand continuously moves downward, opposite to the water's direction, allowing dirt to cling to the sand surface. At this stage, the water appears cleaner but still contains countless microscopic particles. Anything larger than roughly 1/10 the thickness of a human hair. Large paddles stir the water as the plant adds two chemicals: sodium hypochlorite, a disinfectant, and ferric chloride, a coagulant. The coagulant causes fine sand and waste particles to clump together into larger flocks, which settle at the bottom of the tank. Although most dirt is removed, the water is still not clear enough for desalination. Next, it enters the cartridge filtration system, the final defense before reverse osmosis. Each housing contains multiple cartridges made of tightly compressed fiber layers with pore sizes as small as 1 to 5 microns, forcing water to flow from the outside toward the center, removing even the finest particles. Microscopic particles are trapped between the tightly compressed fiber layers of the cartridges, while clean water passes through the cartridge walls and continues onward. When a cartridge becomes saturated, engineers remove and replace it to ensure the system operates at maximum efficiency. The seawater then reaches the most critical stage, separating salt from water. Salt is difficult to remove because its ions cling tightly to water molecules through electrostatic attraction. To break this bond, the system applies extremely high pressure in a process called reverse osmosis, RO. Water is forced through an ultrafine RO membrane, leaving salt and other impurities behind. High-powered centrifugal pumps generate this pressure, with each component controlling a specific stage, gradually increasing as water moves through successive compression phases. By the final stage, pressure reaches approximately 60 bar, about 60 times atmospheric pressure, enabling the production of fresh, desalinated water. The pressure generated in the RO system is strong enough to separate water from salt at the molecular level. After the first stage of reverse osmosis, the water is nearly salt-free but still contains trace ions and microminerals that must be removed to meet strict drinking water standards. It is therefore sent through a second RO stage, where even finer membranes operate under lower pressure but achieve higher salt removal efficiency. This stage reduces the water's electrical conductivity to extremely low levels, stripping out remaining ions and producing truly purified water. The result is an ultra-clean stream with near-perfect purity, ready for remineralization or distribution. While this water is safe for irrigation, its pH must be adjusted for human consumption. The plant balances pH by adding a small amount of acid or a neutralizing solution. Because RO water contains far fewer essential minerals than typical drinking water, trace minerals are added to improve taste and overall quality. During remineralization, essential minerals like calcium and magnesium are added to restore the water's mineral balance, adjust pH, increase alkalinity, and improve taste, creating water that is safe, healthy, and pleasant to drink. Once desalinated, the water is delivered through a modern pipeline network across Saudi Arabia. However, the cost remains high, around $5 per cubic meter, compared to just a few cents in the United States. Now you've seen the entire fascinating process. Stay tuned for more exciting videos, and we'll see you next time.